Hey everybody, this is Time Travel Beard, and this is episode 3 of how to make Minecraft shaders. Today we're going to do vertex shaders, actual lighting and shading, and some fog and stuff like that. So first, for some concept, vertex shaders come before the fragment shader, and they've pretty much got two main purposes. As we said before, the fragment shader draws every pixel on the screen. In the case of 3D objects, it's drawing each pixel of each polygon. For anyone who isn't really familiar with 3D graphics, if we've got a block, it's made of polygons, like it's made of sides, like this is a face, this is a face, this is a face. On the graphics card, they're probably split up into triangles. That doesn't really matter. It's just we've got these different sides of shapes, and if it's something with a circle, which we don't really have in Minecraft, it would still be broken up into like a lot of little squares or triangles that make up that shape. What the vertex shader does is, the first thing it does is it takes the vertexes, which each face like this is actually made of triangles, let's say. So the vertexes are the corners that connect the lines that are the pieces. So if this was split like this, these three vertexes would make this triangle. And the vertex shader takes our little model of everything. Like here's a little T-posed guy, like you might see if a game glitches. And he's just off in his file, whatever. But we've got our camera over here. Like let's say this is looking down on us. Here's us. And here's our camera, and it looks this way. What we've got to do is we've got to get this guy in front of the camera and then centered on the screen. Like let's say this is what our view actually looks like down here, and there's nothing there. So we have to take all his vertexes, move them into the world first to like where he's supposed to be, and then we move the whole world into the camera's view. So let's say here's us on the world and he's right here. So we've moved his vertexes there, and then we have to move those where they look on the screen. So from our view, here be here, but let's say he's looking sideways a little, so his arms are kind of diagonal. So the vertex shader moves everything onto screen. That's the first purpose. The second purpose is that since it comes before the fragment shader, which is where we draw the pixels, it's kind of the intermediary to get data from Minecraft, and that data is stored in each vertex when it's pushed over. So anything we want to do in the fragment shader where we're drawing things, we need to have that data from the vertex shader, since that's where it gets it from Minecraft. So from Minecraft through vertexes, and then we get it into the fragment shader. Now when we have data in the vertexes, and we saw these as varyings, the reason they're called varyings is because they vary over the face of the face, like this face. So when we're sampling a pixel, one pixel might be here, one might be here, one might be here. So if we have something like a torchlight value, like let's say here's a torch, it's really bright here, it's not as bright here. So if this is a value of 3 brightness and this is a value of 2 brightness, then in the middle here would be 2.5 brightness. And this one over here might only be 1 brightness. So in between the 2 and the 1 would be like 1.5 brightness. And that's how torch blocks have that smooth look, is it takes the value here, the value here, the value here in the vertex, and when it passes that as a varying to the fragment shader, it's blending it and varying the value. So anything that we want to have that we're getting from Minecraft, which will also cover those today, like uniforms, attributes, and if there's another word for them, a lot of those we get in the vertexes if it's something that varies over the face of the block. And there's some that are just the same, like a fog color isn't going to change. The color just is what it is. The time of day is the same. That can kind of bypass the vertex shader and go straight to fragment. So that's the concepts of today. We're going to look at vertex shaders and data from Minecraft, like we're going to do fog, probably, and we're going to do some lighting code, which should be kind of fun. So we'll both look at the default Minecraft lighting, which is based on torches and skylight, and then we're going to do some fancy lighting. Okay, so let's get in. If we go to our Notepad, first thing we're going to do is we're going to do close all, so we have a blank slate. And we're going to go to our Minecraft folder. And we're going to go into shader packs, take our tutorial 2, copy and paste it again so we have a working version. And we don't lose our working version. We're going to name this tutorial 3. And this is what we're going to work in today. So tutorial 3, shaders. And let's start with GBuffer's terrain, since that does the terrain. And we're going to look at the vertex shader and the fragment shader. So let's start in the vertex shader. I don't want to use Visual Studio. Let's go back in Notepad. So we're going to edit with Notepad++. And let's also, while we're here, we'll open, and now it's got us in the right folder. Let's also open GBuffer's terrain fragment shader, FSH. So FSH, the fragment shader, is where we were doing all of our stuff so far. And remember from last time, it's got this shadow stuff already from this tutorial. We're going to get rid of that in a minute and just do without it. But first, let's look at the vertex shader and see what's here. So attribute MC entity attribute is data coming from Minecraft that varies. Like, it's not the same on every instance of this, so it might be different for every block. MC entity, we can see here, if it's doing a certain thing, it's doing something to the light. We'll get into that later. That might be the next episode. But we've got these uniforms that are data coming in from Minecraft. Map4s and all this. This is space stuff. We're not going to mess with that today. We've got something that's the shadow light position. That's valuable information for shading. That tells us where either the sun or the moon is, whichever one is casting light and shadows. And then here's varyings. These are the things that the vertex shader is passing to the fragment shader. It's something called LM chord, text chord, GL color, and shadow position. So in this tutorial, the shadows data is calculated in the vertex shader and then passed forward through that. GL color, we can see here in void main, is taking from something called GL color. Most things that start with GL like this are coming from OpenGL. In this case, this is the color of the vertex. In Minecraft, that's used mostly for grass. The way that grass and leaves change color based on biome. That's encoded in this. And then the actual texture is just black and white. And that's why we saw in here, when GL color comes into the fragment shader, we're taking the texture color and multiplying it by that. Because then if the grass is green, the black and white texture will be green. If the grass is brown, in like a desert, it's going to be brown. This is all shading stuff. LM chord is the Minecraft lighting. So we're in vertex shader. And you see it's taking GL texture matrix 1 times GL whatever. This is just how we get the values of the Minecraft lighting, is this little mess right here. And then since that's turning into LM chord and that's in a varying, that's going to be passed into the fragment shader, and into the fragment shader we do stuff with it. That's enough kind of talking right now. Let's get into this, and let's open up our settings too, because we're going to do some settings. First thing we're going to do is we're going to do a define, and we're going to say, call this lighting style, because we're going to use this to save the old lighting so we still have it, and then work on some new versions. So we'll do 0 as a default since we're going to save the old lighting, and let's put 0 and 1 for now, and we'll add more later. And let's copy the lighting style so we've got that. Save the settings. We'll go into our shader.properties, and we're going to add that there on screen. Save that. And then let's come back to the GBuffer's fragment shader. Regardless of what we're doing, we want to use the color and the LM chord, which is the Minecraft lighting data. So we're going to leave those here, and then below that we're going to do our little hash sign if, and we're going to say if lighting style equals 0, and then we're going to keep all this stuff there. And And then down here, let's do our little end if. And to make sure that we remember where things are, we're going to highlight all that stuff and hit tab so that it goes up inside of this if, so we know how things work and remember how they work. And then let's make another one, and we'll do hashtag if lighting style equals 1, and we'll open this up and we'll do an end if to close it. And let's save this and make sure that it works in Minecraft before we do anything else. So let's go to shader pack list, tutorial 3, apply it. And it seems like I'm here where I am. Let's make sure the shader still works. Put up our terrain gray amount. Okay, that works. And our red entities, let's turn those on. And I'm going to go in here and grab myself a cow egg, the great mythical thing. And oh, there's a cat. Okay, cool. So our shader still works. So now let's go into lighting style 1. And this is where we're going to make our new lighting. Now before this, we've got the color already is loading, and it's multiplying by GL color. If we get rid of that GL color, let's do that and save and look at what it does. And to see this, we're going to have to turn off our grayscale setting. You can see now this is what the grass textures look like, is they're just black and white. So when we multiply by GL color, we get that GL color. If we want to just see that GL color on its own, we can have our color just equal GL color. So let's try that for a second. We'll comment out where it loads the texture and have it just equal GL color. And we can have things come down to the next line. It doesn't care about that. So that can actually be a convenient way to kind of have options if we wanted to go like this, and we can kind of comment out and jump between them. So now our color will equal GL color. Let's save that, go back in Minecraft, hit R to refresh, and this is what the GL color data is. So you can see that these leaves are green, these vines are green, but when we do this, we're not getting the where things are see-through and everything. You see the shadows still are because we didn't change the shadow shader. So if we wanted to, we could even say color equals GL color, and then we could say just color dot alpha. Let's put this on one line. Dot alpha equals the alpha from the texture, like this, and then we should get the color from the vertex and just the alpha value from the texture. So now we're mixing data of what we get from Minecraft, which is the vertex color, and texture data to do something. Isn't that kind of cool? It's a weird way the world can look, but it's a good way to see what it does. Okay, let's see. So we are in gbuffer's fragment shader. I'm going to get rid of that line and put this back to being what it was. So our color equals the loaded texture times the vertex color. Now let's go to our settings in the shader, and let's turn lighting style to 1 to be our new lighting that we're making. Now if we look at this right now, all it's doing is loading the textures, and it's applying the LM code, I think. Let's go in here and get ourselves a torch so that we can play with lighting and see about lighting. If we put down a torch, let's see, does that do anything different? Let's get somewhere where it's dark. We might not have any shading going on at all here. Actually, I'll set it to nighttime. That should help. Okay. Now if we look at nighttime, it's not dark. There's no torches, because our new lighting style doesn't do anything. All it does is load a texture value. So let's see what we're doing. we've got our color loaded times GL color, and we've got our light map loaded, the Minecraft data, into a vec2, let's call it LM for light map. But then if we come down to our lighting style, we don't do anything with it. We could look in this shadow tutorial and see what it's doing, but what we're going to do instead is we're going to play around with it and think how Minecraft might use the lighting value. You see here it's taking the color and it's timesing it by the light map. Let's look at that first and see what that does, and then we'll break it down. So copy that and paste it here, and we're going to take our color and multiply it by light map values. The way that would work is if something is in a room with no light, like black lighting, it would be black. If there's white light, it would be white. If there's only red light, it would only be red. Let's save that, see what that looks like. Reload. Okay, so now we've got darkness where it's dark. We've got brightness where there's torches. So we've got some basic lighting now. The way this works in Minecraft is this texture 2D is loading a thing. It's loading a 2D texture called light map. And the way the light map works is it's got two coordinates, an X and a Y, for where it is on the screen. And basically in one direction is how bright the torches are, and in one direction is how bright the sky light is. And then those colors change in Minecraft on the time of day. So something that has high exposure to the sun would be maybe like purplish at night, but it's going to be a bright blue in the daytime. If we want to visualize this differently, we can, instead of loading that default texture, we can do something else with it. So if we want to say vec3 torch color equals vec3, because this is 3 components, and let's make this yellow, so that would be 1 red, 1 green, and 0 blue. Let's put our semicolon, and let's say vec3 sky color equals, and we'll do vec3, and this is going to be very ugly. Just for testing, we're going to make this just a dark blue, so 0, 0, 1. And instead of doing that, let's say our color equals color times and let's check if our color is a vec3 or a vec4. It's a vec4, so we'll do color.rgb equals color.rgb, because we don't want the alpha changing, just the red, green, and blue. And let's do that times torch color, and if we just do this, our torch color is just the same everywhere, so we want to know what it is for each block. So we're going to use the light map. So let's say times torch color times the light map, and either the X or the Y is the torch and the other one is the sky. So let's see what this does. Let's go into Minecraft and reload it, and it looks like yellow is where there's torches, because where I put a torch it makes yellow. Cool. So X is our torch value. But we want to also use the sky, so we'll multiply it by that torch value plus sky color times lm.y. And let's look at this. Go back in Minecraft, refresh it, and there we go. So now we have blue everywhere that there's sky, and where there's torches it also adds yellow. And this isn't the best right here, because we can see the sky actually isn't blue. That's why using this light map can be very valuable. So let's bring that back and get rid of this. And we'll do file save and look at that again. Let's load back into Minecraft. And now since it's using the light map texture, the color of the sky lighting is going to adjust dynamically to match whatever the Minecraft sky is. When we do something fancy later, we can calculate those colors on our own, and we can do something like have sky color. Actually, let's do it right now. Let's bring back this new code, comment out this old code, and let's have the sky color change based on the time of day. A way we can do that is using these uniforms that come from Minecraft. It's not only textures, but we can do other things too that we can find on the iris documentation. One of them is uniform, let's say float. Let's see, sun angle, I believe, is one of them. And we'll find out if this is right in a minute. So this is pulling the uniform from Minecraft. And the way this uniform works is it's 0 to 0.5, like halfway for day, and the other half is night. If I remembered it correctly, we'll find out. So let's say, we'll do an if here, if sun angle is greater than or equal to 0.5, close that bracket, because we want this to happen if that's true. We'll open and close our bracket. So if sun angle is greater than that, which would mean it's nighttime, we want our sky color to equal 0. And then we're going to do our color here. Let's save this. Get back in Minecraft, reload it. And we messed up somewhere. Let's copy our error. I probably have that's probably not a right uniform. File new, paste. Here's our error. I don't know what that is, but we didn't change much, so we know where our problem is. Let's see, if sun angle is greater than 0.5, do this. So we wanted sun angle. It's time to look online. Let's go to the Optifine docs. Shaders.txt, and we're going to find in page, and let's type sun angle. Okay, uniform float sun angle. So that looks like that was right and that wasn't our problem. So let's see if we did something wrong here. I'm going to delete this new part that we made. Save. Try to load back in. Okay, so that part is our problem. Let's paste it. We can comment out this line and see if that's the problem. Go back in here, refresh. And it's fine without that line, so that line is the problem. So what did we do? Well, sky color is a vec3, and here we're just setting it to a float. So if we want it black, it has to be a vec3 of 0, not just 0. So let's try that. We'll save it. Reload. Okay, now it reloaded. So let's see, we've got blue sky. Let's set our time to something in the middle of the night, and now we have a black sky. Cool, so that worked. If we wanted to do a custom sky color like this, we would probably want this to blend and do better. That's math and stuff that will... Let's do it right now, actually. No, I'm going to focus on shading. So we're going to delete that. We'll keep this stuff here in case we want to use it later in another part. Actually, I'm going to control the Z a few times, bringing that all back. Put these together as one option. But comment them out for now because we're not going to use them. Maybe we'll use them later when we do something fancy. And we can take this new stuff and put it inside of this comment. And just like we can comment with these two lines, and that does a line, if we comment with a slash and then a star, everything after that is a comment until you do a star and a slash. So all of this is inactivated right here. So in our new lighting style, we're just doing color times the light map, since the light map gives us that stuff. But maybe we want to change our torch color. So let's actually mix some of the code together of taking the light map and that. We're going to do color times equal, let's see, the torch color was which? It was the lm.x. The sky color is what changes dynamically. So let's keep our torch color. First we'll define that. And we'll keep this formula. Let's copy that and paste it out here. And we want to keep the torch color, but we want to change the sky color. So let's put that down a line, and we'll tab it in so we know it's a part of that. And we want this part to be the texture from the light map. So let's take that and put that where sky color is. And we're going to take just the Y component. And we don't need this anymore. And then now we've got our custom torch color, which is yellow. And then we're multiplying the color, which is already the texture, with the vertex color. And we're going to multiply that by, let's make this a little easier to read. The torch color times the torch value, and the light map sky color times that value. And let's see what that looks like. Cool. So now we have our custom torch color and the Minecraft sky color. Now if we want, we can make this torch color be something that the user can control. So let's go into our settings, and we'll define these. We'll take 0 to 1 values here, like we did for this other stuff. We'll copy that, and we'll paste it. And if you want, you can make this have more values, like 0.1, 0.2. And let's name these torch red. Just an R for red, because we're lazy, we don't want to type too much. And we'll do G for green and B for blue. And we'll say the default would be 1 red and 1 green and 0 blue. Then we're going to copy these. We're going to save our settings. Go into shaders, properties, and we're going to make these sliders. So we'll put them here. And then we also want these to be on screen. So we'll put them here, and we might organize this screen a little bit. And now we want to do something with these. So we're going to take these values, and in our gbuffers terrain, we're going to say this torch color. Let's expand that. So what we can do is we can put this down like this if this helps us think. And we're going to have that instead be a vec3. Oh wait, never mind. We'll keep it as torch color, and then here where we define torch color, we'll have this vec3 be these 3 values we just made. And we will separate those by commas. Let's save this. Get back in Minecraft. Reload it. And right now it looks the same, that's yellow, but let's go into our shader settings. And let's say that we want our torches to be blue, or just white. If we mix all 3, they'll be white. If we want our torch to be blue, there we've got blue torches. If we want purple torches, that's full red and blue with a 0 green. And there we go, we've got purple torches. Nice. I'm going to reset everything so we're back to normal. And now we have custom torchlight. And if we go back to the daytime, oops, I've got caps lock on. We can see that the sky color is adjusting. So now we just learned about skylight and torchlight. And the skylight, the way it works is like when you're in a cave or something, that light kind of fades off the further you get away from the sun. So like here it's darker. And it kind of just comes straight down and then kind of fades off to the side. And that's the default Minecraft lighting, is that skylight and that torchlight. And then if we want to do fancier lighting like shadows and lighting from the sun, what we're going to do, and I'll draw a picture about this, is the way that standard lighting works in most computer graphics, because it's how it works in the world, is if here we have our cube, my great Picasso cube, and here we have a circle. And this is basic computer graphics, like theory and stuff. Here's our sun. The way we calculate lighting is that if something, let me get a blue here for this, is that stuff that's facing the sun is brighter and stuff that's facing away from the sun is darker. We probably all know that. If you don't, that's how that works. So like with a circle, it's like this. It kind of gets darker as it starts getting further away. So this end is all like really dark. This end is kind of light. Same with the square. If this end is facing the surface of it, it'll be bright. If this is kind of facing it, it's going to be kind of dark. and then the one on the opposite side is going to be like pitch black. And the way we compute that in computer graphics is with something called normals. Since each of these faces is 3D and it's got vertexes, those vertexes are a vec3, which is a point x, y, z in space, but also this surface points in a direction. Like this one is facing up, this one is facing this way, this one is coming towards us, and on a circle, each one is going to just look away from the center. It's like a table. The top would look up, everything on the side looks certain ways. So what we do to do lighting is we compare this angle to the angle of the sun, because if it's looking right at the sun, it should be fully white. If it's looking away from the sun, it would be fully black. And actually, if it's even just looking perpendicular, that would also be black. So to calculate computer graphics lighting, what we're going to do is we're going to take the normal, which is this, from the surface, and we're going to take the direction from the sun, and we're going to compare the two. And the smaller this distance is between them, the whiter it should be, and the bigger that distance, the darker it should be. So this one again would be very bright, this would be black because it's perpendicular, and this one would be more than black if it's possible because it's looking away. So to do that, we're going to take this direction, this direction. This one's longer because the sun is really far away. This one is always of length of 1. So we're going to normalize this, which means we'll take the same angle but make it only 1. And then we can compare this angle. Now you could do that with like the Pythagorean theorem, but you could do that with like distance, but there's a very fast way computers do it called dot. And it's probably in here already. I think it did it in the vertex shader, but we'll do it here. We're going to use another uniform. We've got these here. We're going to use one called shadow light angle, I think it is. Let's check our Optifine documentation and make sure that it exists how I think it is. We'll look for shadow light. And here we have a uniform vec3 shadow light position, which is the shadow light sun or moon position and eye space. So let's copy that. We want that information from Minecraft. So we'll paste that here. We'll copy the name of it. And what we're going to do here is we're going to compare the face normal to the sun normal to get sun lighting. But we'll do that in, let's say, lighting style 2, because lighting style 1 here is kind of just default Minecraft lighting. So we'll paste that down here, and let's grab our little thing here, paste it here, and we'll make if lighting style equals 2. Close that with an end if. And this has to have all of our shading stuff in it. So what we need to do is we would still take our torch color because let's say we still want torch color, so we'll put that in here, and then we want our color to be multiplied by torch color, and instead of the light map, let's take the something with the shadow light position. So let's see, this line was our torch lighting, this line was our sky lighting. What we'll do is we'll comment that out right now, and we'll instead take the dot product, which is comparing the two angles, and we're going to compare the shadow light position. Like I said, we need to normalize that, because when we do dot product, we want things to be only 1 long, and the sun is probably further away than 1. So we're going to compare that. So we're inside of dot. The first thing is the sunlight position, let's say. The second one is going to be the normal of the texture. That might just be GL normal or GL normals. If this isn't, we're going to get an error, and I'm going to look it up in another shader. And we want to make sure that this value is a 0 to 1 range, since light is only going to be 0 black to white. being 1. So we're going to take this whole thing and put it inside of a clamp. Clamp is an OpenGL function that limits something. It clamps the value between two things. So we're going to clamp this between 0 and 1. Otherwise, we'll get negative values of brightness when something is facing away from the sun. And let's save this and see if this works. And this should give us lighting towards the sun and towards the moon. Oh wait, we didn't make lighting style 2 be an option. So let's go back to our settings. And we have lighting style 0 and 1. We'll add a 2 in there and save it. And then now if we get back in Minecraft, reload our shader pack settings, let's put lighting style to 2, unexpected token, so we've got something going wrong. So let's look at our code and see what we did. Okay, so it's times that, and it needs to be plus this, so let's do a plus. See if that does it. If that does it, I might have remembered things correctly. If not, we'll need to look stuff up. You always need to look stuff up. So it says we got an error. Let's go to our new and paste it. And it's not giving us information that we can really use. That's oh, I typoed here. I wanted that to be GL normals. Let's see if that does anything. It does not. So I'm going to, let's see, look somewhere else. Let's see what we've got in here, if this does anything. We've got GL, here we go, GL normals like that. Let's see if that exists in the fragment shader as well. Looks like I was missing a capital, and I put an S where it shouldn't be. Okay, it doesn't want to do that. Now, that means that geonormal is probably only available in the vertex shader. So we're going to take it and pass it forward to the fragment shader. So what we're going to do is we're going to create our own varying. And we'll call this normals for the face. And then here we're going to have that equal the GL normal. Oh, I messed it up. This needs to be, what is it? It's a vec3, let's say. And then we'll have normals face dot xyz equals GL normal dot xyz. Okay, I took a break because I messed something up. Let's get back into this. Okay, so in gbuffer's vertex shader, we've got our varying vec3 normals face that we're going to take this information of the normal map, the information of which direction each face is pointing, and we're going to have that equal the GL normal, which is the way it's facing just in its model or wherever it is, rotate it and everything in the right way, normalize it so it's 0 to 1, and that's what we're doing in the vertex shader, and we're passing it with the varying. And like I said, in the newer ones it should be an out. In our fragment shader, we are taking it in as a varying, and then what we're going to do is we're going to say that the distance, or the dot product between the light and the thing would be, again, a 0 to 1 range of the shadow light position, which is the sun or the moon. The dot product compares that to our normal's face. And then we're going to take that and we're going to add that in right here, so that our color is our color times the torchlight plus this sun direction, which is the dot product of that. We can also just take this and put it in there if we wanted to. Just kind of put that there and do this here. But we'll keep it separate so that we can maybe make adjustments to how bright we want the torch color and this and that. Let's see, that line is where I had it inside of there. So we have our color is the color times torchlight plus the light dot. Let's save that. Go in Minecraft, we'll refresh it, and we see if the sun is over there, we have light and things that are facing it. If we do time set to like around noon, where the sun is facing up, and things are lit when they're facing the sun over there. And if we do time set this, then when the sun's over there, only things facing it are lit. And that's your basic shading, is just comparing the angle of the face to where the sun is. But with this didn't have shadows, so down here there's light coming where it shouldn't be. Whereas if we go back to lighting style 0, which had the shadows built in already, sunlight probably isn't getting down in there. But you see, this is much less dramatic. It's got light in the shadows and everything. Yeah, had some configurations for that. So let's go back to our lighting style 2 that we just made. And in our code, let's add back in the skylight, where things have light rather exposed to the sky. And then we've got light for where the sun is. Let's see what that looks like. Okay, so now we still have this dramatic lighting, but we also have some brightness on these ends that are looking towards the sky. It looks like these things pointing in the opposite direction are still kind of black, so maybe we didn't clamp this right. We did not. So let's clamp this between a 0 to 1. 0, 1. And what that does is it makes it so that the lowest it can be is 0 and the brightest it can be is 1. Because otherwise, if we compare these angles, all these ones pointing away are negative values, and that would make things darker than they should be. So we come back in here and load. Now we can see that these parts pointing away from the sun aren't negative black, but they're just the sun exposure or the sky exposure to them. So cool, now we just made torchlight and skylight, and we have sunlight. And we did this on our own, but we didn't do the shadows yet. We've already got that code in the other thing, and we'll go over that in another episode. Let's look at fog real quick. I'll scratch that. So to review what we're doing in lighting in our new lighting style 2 is all that the shader is doing is first it's loading the texture, and it's multiplying it by the vertex color. We're taking the light map chords, and we got all of these things from the vertex shader. We're also taking the normals of our face, which we got from the vertex shader. And what we did is we took the vertex data by its matrix, which put it into the camera view, put that in a 0 to 1 range, and then we took that 0 to 1 range and we compared it to the position of the sun, which was also in a 0 to 1 range, did the dot product, which does that comparison, clamped it between 0 to 1 to give us that light dot, and then that gives us our sun lighting. So here we have torchlight, here we have skylight, here we have sunlight. And as we saw, by taking the texture value, we get a dynamic sky color, but we also, if we wanted to, could do our own sky color and make it up and then change it based on different things like sun angle and that. And there's a lot of other things we can do with information like that, which is why you want to be familiar with these documentation, because a lot of them kind of are multiple similar things. So if we did just the sun position, we wouldn't also get the moon position when it switches. This gives us both at the same time. We can also have an up position. So something we could do with that is we could say maybe we want the skylight to only be on things facing up. And there's all kinds of other stuff we can do in here. So you can just search and look for things and find stuff. Next episode, I think we'll do fog, and then that might get us to more of a regular shader. There's also things like world time, moon phase. There's all kinds of things that we can do cool effects with when we want to. Held items. Like, all of this stuff is information we can get from Minecraft that we can do things with. So we can make night vision effects, blindness effects, all kinds of stuff.